integrate low 6% of small capacitor inverters to a transformer, and you are able to achieve a high voltage in the secondary side. So when you want to operate an application which requires high voltage by using multi-pulse inverter, our problem is resolving. But what happens? The inverter bulky nature is increasing. When you go for transformer, again what happens? Already the transformer will have the losses. For a transformer, when you give a non-sinusoidal voltage for transforming, you know that when we go for sinusoidal voltage, I mean, as an electrical engineer or process user, for a transformer, when we give a sinusoidal voltage and when we give a square wave voltage, what will be the difference that we find? In which case the transformer will heat up more. A transformer is there. Let us take a considered power transformer, where we give a sinusoidal voltage with the same voltage, peak voltage, if we give a square wave. In which case the transformer will heat up more square wave. In fact, the reason is simple. When you are giving a square wave voltage to a transformer, it means same thing. You are giving all those voltages to the transformer. Every component of your voltage is going to again create a circulating current, because fundamental component creates its own voltage on the lighting, back EMF, and current flows. Similarly, your second order harmonic, third order harmonic, right? So every harmonic voltage which you are injecting into the transformer is going to create its own harmonic current, and it is circulating in the transformer. But what the user uses only fundamental component which appears in the secondary side. And you know the magnetic saturation, because when there is continuous rate of change of voltage or current in a system, in a magnetic circuit, it doesn't come to saturation so easy. But when you are injecting a harmonic current or DC component currents into the transformer, the magnetic saturation appears early and it will lead to losses. Simple example. When you find a winding, you have a winding and you have a DC voltage. Let us now just forget about transformer. A DC voltage connected to a winding. So your voltage started from zero. This voltage which is going through your this one start giving some pulse. Let it be stationary first, whether it's AC or DC, whatsoever. Your voltage is increasing more, current increases more, flux increases more. Flux means the flux that is coming more from the winding. If you keep on increasing voltage more and more and more, current increases. After it reaches to the saturation point, that is current saturation point, still if you increase the voltage, what happens to the flux? Constant. But after you make the magnetic flux constant, still if you increase the voltage, current decreases. Let us say winding has the capacity to take the current. So it doesn't work. The current flows in the winding still. So what happens after magnetic flux reaches to saturation? It starts, because once it is taking energy, it should dissipate. So automatically the energy up to saturation level is more concentrated to release the flux. But once the flux reaches saturation, to compensate the power in and power out concept, what it start heating. So the energy that is inside the winding will start dissipating in terms of heat, because flux got saturated. Same thing happens in the transformer. So that is the basic thing. That is, already a transformer will have its characteristics and it have its losses. But when you give a harmonic component to a transformer, its efficiency much more reduces. Your cost of the equipment is increased. So then we need to go for some or other way where we are able to remove the transformer. And that's where we go for material inverters. So simply, if we talk about what is a material, because see, now when we go for enhance the complexity of the circuit to address some or other application, ultimately problems also arises. When the problem arises and when you want to compensate the problem, you need to use a controller. So first thing is, what we should know is, what is the advancement required, what is the necessity of advancement, and when we advance something, what are the problems that we are getting into the picture, and that problems, how can we do in the controller, that's where we need to work out. So now, the technology of the two-layer inverters has been enhanced to multi-layer inverters, as you are seeing on the screen. It's a simple concept, that is, as you have seen earlier, we have a VDC, and we are just getting, we have only one switching operation, something like that, and we are getting either V or V by 2, V by 2, 0 or V by 2. V, 0, minus V. That's what we have seen, in the last. But in the case of multi-layer inverter, general topology, what happens? You have this type of technique, where if you have series of switches, and if it is the total voltage V, which that is, it is VDC is now a high voltage, then what happens when you are connecting the capacitors in series of same capacitance value, what happens to the voltage automatically divides into equal parts. And each equal part of capacitor voltage is processed to add the voltages are aligned by switching mechanism to achieve the step voltage output at the output side. So what happens? Your voltages instead of increasing all of a sudden from 0 to V, it increases to V by 4, then a step V by 2, then a step 3V by then V. So what happens? The step voltage will be more sinusoidal. But on the other side, now you should understand that the V can be 4 times of V. Because every switching, so earlier if it is only one voltage V, now you are able to enhance to 4 times of the voltage. But with the same circuit, without any transformer, you could achieve the high voltages. How? Basically, when we talk about multi-layer inverters, basic thing, like now you open the literature and you go through the controller operated in the inverters, you might be seeing so many type of